I am your friend Rahul Saigaonkar. Let's continue our discussion of NCERT Science series. We are discussing NCERT Science textbook for class 10, and today, interestingly, we are discussing chapter 10 as well. That means class 10, chapter 10, light, reflection and refraction. Today is the beginning of new topic or new dimension. Now, before this, we have discussed from chapter 1 to chapter 5, where we have gained insights into basics of chemistry knowledge. From chapter 6 to chapter 9, we have mainly discussed some important topics connected to biology. And from today, I would say from chapter 10 to chapter 13, our discussion predominantly would be gaining knowledge about physics topics from this NCERT textbook of class 10. And at the fag end of our discussion, we'll talk about environment, that chapter 14, 15, 16, connected to environment, natural resources, energy, etc. All right. So today's interaction is about light. We'll focus on reflection and associated topics with it. We'll talk about refraction as well. It's a very important topic where many questions have appeared in UPSC Civil Services Prelims, where you need to understand these topics so that it becomes very easy for you to attempt those MCQs. I call these MCQs from general science as freebies. People should not commit mistakes there. The only thing is that you need to understand things so that it becomes very easy for you to eliminate the choices and arrive at the right answers. All right. Now, before this also, before this chapter 10 of class 10, we have already gained some insight into light, into the ideas of reflection, multiple reflection, different kinds of mirrors, etc. All right. This is not our first interaction. We have already discussed class 6, class 7, class 8, class 9. And there we have understood light is extremely important for us to see things. And where do we get this light from? The ultimate source of this light is our star, that is sun. So we have understood what are luminous objects. Luminous objects are the ones which have their own light, which give out their own energy. Sun is one of the luminous objects. We discussed that moon is not luminous. Moon simply reflects the light from sun. So we discussed about luminous objects, non-luminous objects. We also understood that light again can be described or can be represented as a ray. And we have understood that if any obstruction comes in between, that obstruction, if it is transparent, then the light would pass through it. But if it is opaque, then the light is obstructed by opaque objects. So we have understood about transparent objects, opaque objects, translucent objects in our previous interactions. We have also discussed about the formation of shadows. Whenever there is an opaque object in between the incident light, or when incident light is put on the opaque object, then a shadow is formed. We have discussed all these things. So we will be building our knowledge over this itself. So you have understood light is extremely important. In fact, in our 9th discussion, we understood that reflection of light is extremely important. Why I am able to see so many things. For instance, I am able to see there are some panels there is a camera there is a desktop, all the setup is there. Why am I able to see all these things? This is because of reflection of light itself. Light is being reflected. We discussed that why leaves are green, because the green light out of the white light, that is sunlight, green light is reflected the most. We see the color as green. So we have understood this phenomena as well. So today we'll talk about two important facets connected with light, connected with optics, that is reflection and refraction. Now, first thing, reflection and refraction. Why do they occur? Now, we have discussed that light can be represented as a ray. And in our previous interactions, we have understood some characteristics of light. The speed of light is 3 into 10 to the power of 8 meter per second. Light has dual nature. We have understood light is a wave. Or light behaves as a wave, and light also behaves as a particle. I simply like this picture a lot because it describes both the things. It spells particle as well as wave together. So light, it behaves both as wave and a particle. Now, right now, whenever we talk about this ray diagram, we discuss light as a particle. All right. But in our subsequent discussions, when we talk about some important physics concepts going forward, we'll talk about the characteristics of light as a wave as well. There we'll talk about the concept of interference, concept of diffraction. Light is diffracted, light interferes because it also behaves as a wave. and when two waves meet, when two waves interfere, they can interfere in phase. The amplitude grows, or it gets amplified. Light can also interfere out of phase, and when it is out of phase, the amplitude reduces. We'll talk about these concepts going forward, right? That's it. That's what is mentioned here. Diffraction, interference, we'll talk about these in higher classes. That means the wave theory of light would be understood in a better way going forward. But right now we do know, or we do have to establish the idea that light is dual in nature, means it behaves as a particle, it behaves as a wave as well, right? So today's discussion is connected to reflection, and when we talk about reflection, we use the ray diagram to explain. When I use a line like this, that means the light is incident. All right, we give a direction to it. So reflection, what is the meaning of reflection? You must have all observed in our day-to-day lives. Take a mirror, you will see your own reflection in the mirror. If there is no mirror also, during the olden times, if you simply look inside a water body, say you're sitting simply at a lake and you look inside a lake, you will see your own reflection in that water. That's the famous story of Narcissus as well, no? That's why the term also has come, narcissistic. Narcissus was a person, Greek person. He looked at his own image in water and he fell in love with himself. That's why the term narcissistic comes, one who loves themselves, right? Narcissistic tendencies, these terms are used, right? So let's not get there, let's not get into that discussion. But why I'm trying to explain is, reflection is very common phenomena that we observe in our everyday life. That means whenever light is incident on something, that light is reflected. And please remember, it's not just a plain mirror. This shirt is also reflecting light, my body is also reflecting light. Some light is incident and it is being reflected. The spectacles, this particular pen, everything it reflects light. All right, except for perhaps the perfectly black body, which completely absorbs everything. So light is reflected not just from a mirror, from other bodies as well. So how is this light reflected? Does it follow some sort of rules, laws? Reflection follows two important laws. Laws of reflection include, first one, that the incident ray, this is the incident ray. Now the respective reflected ray is this, the incident ray, the reflected ray, and the normal to the surface from where the reflection is occurring, the normal to the mirror. Now this is how we describe a mirror in optics. If you just draw hashes or the inclined lines below, that means this surface is not going to reflect, the other surface is going to reflect. That means this incident ray, reflected ray, and the normal to the reflecting surface, they must all lie in a same plane. That means these three are in same plane. They have to be in same plane. Right now I would say they are in the plane of this particular panel. The second law, it says that for reflection to occur, the angle of incidence is always equal to the angle of incidence is always equal to angle of reflection. And please remember that angle is with respect to the normal to the mirror. All right, to the normal to the mirror. That means, let me just erase everything and let me try to explain it again. See, now if, let me take the board. Now if this is the mirror surface, you know that this is the incident ray, this is the reflected ray. And when we draw a normal, let me draw the normal with a different color, let me draw it with blue color. Now please try to understand, I am not telling that this angle is equal to this angle. No, it's absolutely wrong. Let me just erase this so that you do not get confused. What we are telling is, with respect to the normal, this is the angle of incidence, this would be equal to the angle of reflection. Is it clear? Now this is the law of reflection, and please remember, for any kind of reflection, this law is followed. For any kind of reflection, this law is followed. Now you must be having a question in your mind. This we have discussed before also. Sir, what if, say, imagine this is the reflecting surface. What if I incident the light exactly normal to it? Then the reflected ray would be exactly opposite to it. That means the angle between them would be zero. That's the basic idea. All right. Now, when we talk about reflection, I told you reflection can occur from any surface. Reflection can occur from any. So I told you this shirt is reflecting, my body is reflecting. If I use a plain mirror, that would also reflect the light. But reflection from smooth surfaces, reflection from smooth surfaces, it is called as regular reflection. It is called as regular reflection. Whereas reflection from irregular surfaces, which are not smooth or probably which are not polished also, not smooth, not polished, or rough surfaces, there also the reflection takes place. Please remember this. Now this reflection, it is called as diffuse reflection or irregular reflection. It is called as irregular reflection. Now, how can you distinguish between the two? It's plain and simple. See, I take a mirror, I can see my own face. But say I look into the water. I give you an example of a lake. I look into the water. I can see my face clearly. That means it is some sort of a regular reflection because water is very, very calm. Now imagine you drop a small pebble in water and then you see your own face. Do you see your own face? You would not see it. That means the images that are formed by smooth surfaces, they are distinguishable. You can identify it. But the image formed through irregular surface, we cannot identify it. The image is very diffused. But please remember, even if it is a regular reflection or irregular reflection, both the kinds of reflection follows the laws of reflection. A very important point. If I simply create an MCQ asking you regular reflection on a smooth surface, it follows both the laws of reflection. Yes. Irregular reflection from a rough surface, it does not follow the laws of reflection. Absolutely wrong statement. That also follows the laws of reflection. Clear? Right. Let's move on. Now, based on this, based on the concept of reflection, we have developed spherical mirrors. We have spherical mirrors in our day-to-day activities or day-to-day lives. Now, you will see that I gave you example of a plane mirror. I give you example of a plane mirror. I said, now if this is the mirror, this is a plane mirror, right? This is a plane mirror, and I say this is the incident light, this is the reflected light. All right, and this is the normal. I'll draw normal with the black ink. This is the normal. Now, as soon as I turn this, now this is a plane mirror. This is an example of plane mirror. But if the mirror has curvature, that means this is the reflecting surface, or if the mirror has curvature, something like this, that means the opposite. This is the reflecting surface. These are called spherical mirrors. Why? Because these are like section of a sphere. Now, if I complete this, I would get a sphere. That's why they're spherical mirrors. The classic example of a spherical mirror would be your spoon. Have you seen a spoon? Spoon has both the sides, right? Spoon has a concave side and a convex side. So spoon, it behaves as concave mirror as well as convex mirror. And we have day-to-day applications of these mirrors, right? Spherical mirrors means mirrors. Once we complete, it forms a circle. Let me just give you an example of this. See, this is a concave mirror. Spherical mirrors can be of two types: concave mirror, convex mirror. Concave, cave, that means the reflecting surface is this is the reflecting surface. Convex mirror, this would be the reflecting surface, the outside surface, the bulge surface. So in a concave mirror, this is the reflecting surface. In a convex mirror, this is the reflecting surface, the one opposite. Please try to understand this. Now, if you're not able to imagine it, let me just give you this example. See, any kind of mirror is like a segment or a section of a sphere. If it is a convex mirror, I can simply complete a sphere or a circle like this. Meaning, for this particular mirror, there would be a center of curvature. So there are certain terms that we need to understand, and I told you the basic kind of mirror is this. You can simply check today itself. Take a spoon. If you see, you will get your own image, and you can observe this also. At one point of time, you will get inverted image, especially on the other side of the spoon. We'll understand why that happens. Okay, so there are certain terminologies that we need to understand here. C, going forward, it represents center of curvature. Means if this is the mirror, if I complete the circle, the center of that circle would be the center of curvature. F is the focal point. Focal point means where the light is focused. It is called as focal point. And the radius from point P, from the edge of the aperture, the center of the circle or center of the sphere, that becomes radius of curvature, and the length is called focal length. From this point, aperture point P, to the focal point, it is called as focal length, because these are used in calculation, although we do not need it from UPSC perspective, but we'll get some insights or some idea about that going forward. Right? So we have two kinds of mirror, concave mirror and convex mirror. Now, the images formed by these can become basis of our question. Now, if it is a concave mirror, remember concave means I simply draw a spherical structure and I need to identify concave mirror based on the reflecting side. Now, for concave mirror, the reflecting side should be the concave side. That means light would be incident from here and reflected something like this. That's why this, the other side, this section, it is not going to reflect. Now, imagine that I incident a light on concave mirror and I place an object is placed. Where is the image formed? Now, if the position of the object whose image is to be seen, if it is at infinity, then the image that is formed would be at focus. Now, these are some ray diagrams. This is the first ray diagram. If this AB is the object, incident light comes and the reflected image is formed at this focus, and you can see the AB image, its height is, say, if I put it as h, then you can see the entire image would be very, very diminished, very, very small. Similarly, if I change the position of the object beyond the center of curvature, then the image would be formed between F and C. That means between the focus and the center of curvature. Again, it would be exactly diminished, and all these images from point number 1 to 5 would be real and inverted. Meaning, if I take the second example, see, now the object is not at infinity. This is the object. AB is the object. This is the center of curvature. Now, the incident light, it is reflected, and then the image is formed somewhere between center of curvature and the focus, and that image is a smaller image. This AB, if it is of height h, this would be less than h and it would be inverted, but it would be a real image. It would be real and inverted. So you will get real and inverted images when you place the object at infinity. At infinity, it is very diminished. If it is beyond C, it is very, very small size, it is diminished. Once you put the object exactly at center of curvature, then the image formed would be exactly same height as that of the object. It would be same height. And if you place the object between C and F, and at F, you will see enlarged images, but all these images would be inverted only. If you look at the ray diagram, you will understand that the images formed would be bigger images. But just focus on the last pointer. If you place somewhere between point P, that is the aperture point P, and the focus point, the image would be formed behind the mirror, and this image would be virtual and erect, and this would be enlarged. Now, by the same concept, if you look at simple plane mirror, you do understand this was the plane mirror. This was the example of plane mirror. The image, I'll just draw it again. If this is a plane mirror, let me draw a straight line so that there is no confusion. This is a straight line, this is a mirror, and incident ray or the object is somewhere here. You will see the light is incident, yes, and the image is formed behind. This is always virtual image. You do know virtual image, and this image would be erect. A similar concept again in the spherical mirror also we get similar kind of image when we place the object between P and F. There is no need to focus too much on these ray diagrams, but sometimes probably in state PSC etc. you might get certain questions. That's why I'm covering that also. Okay, now very similar to how concave mirror images are formed. If you look at convex mirror, you will see that the object, if it is placed at infinity, then the image is formed at the focus behind the mirror. It is highly diminished. That means in both cases of convex mirror, if you place between infinity and pole anywhere, you will always get diminished image, and you will always get virtual and erect image. Let me just show you the ray diagram so that you understand. This is the convex side. Whenever light is incident, the light is reflected and the image is always formed behind the lens. Image is formed always behind the lens, and the image would rather be diminished, but it is virtual and erect always. All right. So with respect to convex, you get only these two kind of cases, because you cannot, the center of curvature is on the other side since it is the convex mirror. Clear? Now You must have seen a lot of uses of this convex mirror and concave mirrors in our day-to-day life, right? We have used so many concave mirrors in our day-to-day life. Say concave mirrors are used in our headlights, They're also used in shaving mirrors because I want to see closely. I want to see enlarged image. I want to see a virtual and a real image. I want to see basically this virtual and erect image which is enlarged, right? So I do use them in shaving mirrors. The dentists also use them. Large concave mirrors are also used to concentrate sunlight. Then the dentists also use it to see the teeth. You must have seen a dentist mirror, a small dentist mirror. It's a concave mirror. The dentist puts it in your mouth and sees the reflection of that teeth to check it. Right? Now, apart from that, convex mirrors, they are also used in many day-to-day applications. You must have seen that if you are driving a car, the mirror that you have, it is actually a convex mirror, and that's why there is an instruction written there. Objects in the mirror, they are closer than they appear, right? And you see a little diminished image itself. Why do you use it? To see the traffic behind you, right? So convex mirror, it enables the driver to see what is happening behind you. I might ask you a question. I can simply use a plane mirror. Can I use a plane mirror also there? I can use a plane mirror also. That is not an issue. You must have seen in movies, etc., where a hero, if that rear view mirror is broken, then the hero would use some sort of a mirror to check, the normal kind of mirror that we have. That is also possible, but I cannot cover wide angle. I want to see the traffic behind me from a wider angle. That's why I use a convex mirror there. Clear? Right. This is about the reflection concept. Now, there can be questions which can be formed like this. A simple kind of question. Consider the following: dentistry mirror, rear view mirror, and torchlight. There are three examples that are given here. Which of the above uses concave mirrors? That's the question in front of you. Take a few seconds to attempt this question and let me know how you did. All right. The options are given here. A is 1, 2, 2, 3, 1, 3, 1, 2, 3. It's fairly easy question. Such questions can be created. Right. Let's move on and talk about the spherical mirror formula. This is again from academic perspective. Spherical mirror formula and magnification formula, they are majorly used in numericals calculation part. For any spherical mirror, be it concave or convex mirror, you need two important parameters or variables. First is the distance of object from its pole. Pole is this particular point on the aperture. Pole, it is called object distance, and the distance of image from the pole of the mirror, right? So from here, at what distance is the object, and from here at what distance is the image. Based on these two distances, we can calculate the this is the mirror formula. 1 by f is equal to 1 by u plus 1 by b, and based on this we can also find magnification of that spherical mirror. Magnification formula is height of the image by height of the object, and of course if the height of image is more, then the image is enlarged, image is magnified. The same formula also can be derived in this form of the object distance and the image distance as minus u by v. Again, from academic perspective, this becomes a little important, not for us, I would say, from UPSC civil services perspective, but just to have some knowledge, we are discussing this. All right. Magnification, common sense tells height of the image divided by height of the object. Right. Let's move ahead and talk about refraction of light. This is a very important concept, refraction of light. Now, what is refraction? Reflection is the incident ray is reflected. The incident ray is reflected. What is refraction? Some amount of light can pass through a medium, and it can change its direction. So refraction basically is bending of light. I would say bending of light when it passes from one medium to another medium. And why this light bends? Light bends because the speed of light changes. Please remember this point, very important. Refraction is the change of speed and change of direction of the light wave when it is passing from one medium to another medium. Now, in our day-to-day life, we have seen it so many times. For example, you simply take a bucket of water and just put a coin in it. You will see that the coin appears to have been raised, or the coin appears to be displaced. Why? It happens because of refraction. Why is that happening? Because if I have a bucket like this, right? Now light wave is passing from air and there is water in it. There are two mediums now. It is passing from air into water, and that's why it appears as if the coin is at some other place. Have you seen this? I'm quite sure you must have seen. And why does that happen? Please remember, the speed of light itself changes, or speed of light, it differs in different medium. There is some variation in different mediums. Speed of light changes as well as the direction of light changes. It either bends towards the normal or bends away from the normal. That is the meaning of refraction. Now, refraction also follows two specific laws. As I told you, the first thing is you need a medium. For understanding refraction, you need a medium. Now, this is the interface. This is the interface. Now, imagine on this side there is air and on this side there is water. As I gave you example of the bucket. That means the light is incident, or light is coming at this interface, air medium, and from air medium now it is moving into the water medium. What will happen is the light will change its direction. The ideal direction for this should be something like this, correct? Because light travels in a straight line. We have known this. We have already built this concept right from before itself, right? So now light, it bends. It moves either this side or it moves towards this side. And this movement, apparently, it depends on the density, or I would say optical density of the mediums. It depends on the optical density of the mediums. Now, what is this optical density? We'll try to gauge that in some time. But I hope that the idea is clear. The incident ray should have moved in this direction, but it has changed the direction to one or the other side, depending on the mediums. That is the meaning of refraction. Now, what would be the normal to these surfaces? The normal to these surfaces would be this particular blue line. Normal means 90 degree at the interface. Now, the refraction, the law of refraction, there are two laws of it. First law, again, very similar to how we have in reflection, that the incident ray, the refracted ray, and the normal at the interface, normal at the point of incidence, they all should lie in a same plane. Apart from that, please remember, now the angle of incidence and the angle of refraction are not same. Remember, the ratio of sine of angle of incidence to the ratio of sine of angle of refraction is always constant to mediums. That is the second law. This is called as Snell's law. This is called as Snell's law. Now, here, if this is the if this is the first incident ray, the incident ray is at an angle of θ1. Now, this is the normal. And now, from this medium, it should have ideally gone in a straight line, but has not gone in a straight line. What has happened is light has refracted to this direction. Now, with respect to normal to the direction, this is the angle θ1, that is angle of incidence. This is the angle of refraction θ2. And what Snell's law tells is this sine of θ1 divided by sine of θ2, it is always equal to some constant. It is always constant. All right, those are the laws of refraction. Now, this n is a constant which is called as refractive index. It's very important. Now, you must see this particular glass. You must see this particular glass. Why am I wearing these glasses? You will understand again the idea of refraction. Through the idea of refraction itself, we use these lenses. What is happening with my eyes? What is the problem is that the image that is formed behind, on both the sides, there is a slight astigmatism. The image from one eye and both eyes, they have to match, right? But there is slight power. I have about 0.75 negative power, not the exact numbers though. But what am I doing through this? What am I doing? I am passing light from here to this particular medium so that they are incident properly on my eyes, right? Properly on my eye, so that image is formed in a correct way behind. Right? Why? Because of refraction. So day to day, whatever spectacles you use, whatever lenses you use, they work on the concept of this refraction only. That's why you must have seen that when you go to an optical place or when you go to an ophthalmologist, what they do is they'll tell you that you have some sort of power in your eye, and they will try to keep a combination of lenses, and then they'll try to gauge what is the exact power to form the correct image. All right, and this lens is made up of particular refractive index. That refractive index for a material would be constant, and refractive index, it is a measure of how much the light slows down or how much the light speeds up when it goes through a particular medium. All right, and refractive index of vacuum is always 1. N of vacuum is always 1, and refractive index for any medium N, it is calculated by speed of light in vacuum divided by the speed of light in that particular medium. That is the basic idea of refractive index. Clear? Right. Now you must be thinking, sir, you gave me one example of lenses, one significance, but refraction is extremely significant in our day-to-day life. There are so many phenomena which depend on refraction itself, which depend on these refractive indices, right? Air has a refractive index a little higher than vacuum, 1.0003. Ice, alcohol, you can see refractive indexes of different materials here, just for your reference. Now, the significance of this is we come to know a quantity called as optical density, meaning how the speed of light would be influenced when the light passes through that particular medium. All right, and that's why if vacuum, its refractive index or its optical density is considered as 1, then any other entity whose value is bigger than that becomes a denser medium. So we try to find out which is a rarer medium, because we need to understand what will happen when light passes from a rarer medium. These are some of the rarer mediums, and these are denser mediums. So what happens when light passes from rarer medium to denser medium, or what happens when light passes from denser medium to rarer medium? We'll try to establish this, and this depends on the concept called as optical density. This is the connotation that we use. Now what happens here? What happens? See, when light passes from a rarer medium, now this is the, say, imagine this is air and imagine this is glass, right? Now glass has a higher refractive index than air, and when the light passes from rarer medium to denser medium, the light, it tends to bend towards the normal. It tends to bend towards the normal. Please remember, from rarer to denser, the refracted ray, it bends towards the normal. Ideally it should have gone like this, but it has refracted in this direction towards the normal. That means what is happening? What happens is the speed of light rays, it reduces when it passes from the rarer medium to denser medium, because speed of light should be high. That's why in vacuum it is 3 into 10 to the power of 8 meter per second. In air, a little lower. In other mediums, it would be a little lower than that. That means the speed of light reduces, and the refracted ray, it bends towards the normal. Now this is a phenomena that you must have seen in many of the swimming pools. Now when you go near a swimming pool, I feel that the water is quite shallow. The water is it's not very deep. It looks as if it's shallow, but as soon as you enter it, you will feel, oh my god, it's very deep. Why does it happen? It happens because of the concept of refraction itself. And the opposite happens when the light rays passes from denser medium to rarer medium. That means the light rays or the refracted ray, it tends to bend away from the normal. Now if this is incident ray from denser, ideally it should have gone in this direction. This is the normal, and it gets away, it gets away from the normal. That means the speed increases from a denser medium. When it comes to rarer medium, its speed increases a little. Now when I say speed increases, please try to remember, when I say speed increases, speed slightly changes, but its frequency never changes. This is a very, very important point. Now, if frequency does not change, that means its wavelength, its wavelength changes for sure, because one of the parameters has to change. So when light travels from a rarer medium to denser medium, or denser medium to rarer medium, please remember its speed varies a little, its frequency never changes, its wavelength changes, and of course speed is changing, is speed and wavelength, they are changing a little bit, frequency always remains same. It's a very, very important pointer from MCQ perspective. All right. Now, sir, I understood refraction, I understood ideas with respect to refraction, but I want to know in my day-to-day life, how is it really significant? In our day-to-day life, in our day-to-day activities, we see so many concepts of refraction. I give you example of this particular spectacle, or when you simply watch a star in the night, right? Star appears as if it is twinkling. Why does that happen? Is the star twinkling? Star is not twinkling at all, but I feel as if the star is twinkling because the light coming from that particular star, it is refracted multiple times when it enters the atmosphere, and it appears as if it is twinkling. So it's actually not twinkling. The twinkling of stars is because of refraction. You must have seen a mirage. You must have seen a mirage, especially on a hot day. On a hot day, you must have seen that on the road, you see that the light appears as if it is bending. You see that as if something is burning, and the light appears very wavy, or the image appears very wavy. Why does that happen? Because of heat. Because of intense heating, what happens is, this is the road surface. Imagine this is the road surface. What is happening is, air which is nearer to this road, it heats up and it starts moving upwards. That means the density of air itself is in layers, and when light passes through this, it continuously refracts, and it looks as if the image is blurry, the image is blurred. You must have seen this in a mirage, or you must have seen the looming of luminous objects. Or see, we have sun. Around sun, it appears as if there is another layer which is not exactly circular. Now, why does that happen? Again, it looks like that because of the idea of refraction. The looming around luminous objects is because of refraction. Some kind of a halo is seen. You must have observed even with your bulbs also. Even if your bulbs are, so this light, I don't see too much of looming right now, but you can observe that looming. A kind of a halo is formed around that luminous object. Apart from that, you must have seen that something in water, it is offset from its original position. I give you example of coin. That is refraction, right? You must have seen so many applications. How do we focus light? How does this work? It is focusing light at one particular place based on the refractive index. So it is working on the concept of refraction. How do I watch through a lens, or how do I watch through a microscope? How do I watch through a telescope? It is a combination of different lenses made up of different refractive indices so that I get a proper image. These are some of the applications. Apart from that, you must have seen that these days we talk about optical fibers. These optical fibers, what do they carry? They carry electromagnetic radiation, they carry light. Can we transfer information also through it? Of course, we can transfer information through that in binary form, and that is what is observed. You must have heard about a term called as total internal reflection. Now, this is actually a misnomer. Total internal reflection is a concept connected to refraction of light rather than reflection of light. All right. Now, let me just explain to you. Now, I told you that when light travels, now see, this is the interface. This is the interface. All right. Now, I told you that if this is the denser medium, say imagine this is a denser medium, and if this is a rarer medium, and I told you if I draw a normal to this, this is a normal to it, and now this is the incident ray. Let me use the blue color for incident ray. Now, this is the incident ray. This is the incident ray, and I told you when this happens, means the refracted ray, it moves away. It moves away from the normal. That means this particular theta1 would be smaller, theta2 would be larger. Now, I play around with these refractive indices to ensure that the angle of refraction, it goes on increasing. Meaning I incident a light and ensure that the refracted wave moves away from the normal. I repeat the experiment. I increase the angle, I play around with the refractive indices, and at one point of time, I would see that at this interface, the refracted ray at one point of time would move parallel to the interface. Yes. And if I further increase the angle, this is called critical angle. If you further increase the angle, there would be a point where this incident ray would completely be reflected. It appears as if it is reflected, but I am ensuring that it is refracted. That's why it's called total internal reflection, meaning the idea is based on the concept of refraction, where I would be playing around with the refractive indices and I would be playing around with the angle of incidence, the angle of incidence. And based on that, I design a pipeline, or I design a conduit through which is made up of different, say here I am creating a conduit of different refractive indices. You can see here there is refractive index 1 n1 here, refractive index 2 n2 here, refractive index 3 n3 here. So what is happening is I ensure that the light is incident in such a way that it exceeds the critical angle. That means this ray would be completely refracted, and I ensure that wherever it is incident, it can be completely transmitted from one end to another end. That is the idea behind optical fibers. That's why you must have seen optical fibers, they have multiple claddings, multiple coverings, multiple claddings of different refractive indices to ensure that no amount of information is lost. That means whatever I send from this side, it is completely reflected inside based on the concept of refraction, and I can receive the information on the other side. That's the total internal reflection. That's why I told you it's a misnomer. I hope it's clear. I hope I have given you good insight into the concept of total internal reflection. Questions can be formed on this as well. In fact, questions have come like this on the topic of refraction, reflection, and in our subsequent classes we'll talk about some other ideas in optics, where we'll talk about diffraction, interference, dispersion, etc. So you'll understand more and more. Questions like this have come where some phenomena have been given: size of sun at dusk, color of sun at dawn, moon being visible at dawn, twinkle of stars in sky, pole star being visible in the sky. Which of these are optical illusions? Now, one of them we have already deciphered. This twinkling of stars is actually optical illusion, because stars do not twinkle. They appear as if they are twinkling, because the light which is passing through Earth's atmosphere, it appears as if it is refracted multiple times. That's why it appears twinkly, but it is actually not twinkling. So it's an optical illusion. So I can eliminate 4. So based on elimination, I do know that this would not be answer, this would not be answer. Or which of the above are optical illusions? So it should have that, all right? It should have that. So the answer would be either this or this, all right? So if you look at the other stuff, you can get answer from that. See, one of the ideas that pole star being visible in the sky, I know that it is not an optical illusion, because pole star is actually visible in the sky because it is directly above the axis of the Earth. So this is not an optical illusion, I know. So I can eliminate this. I do get the answer very easily, right? So questions like these have come before. So make sure that you are thorough with the ideas. You're thorough with the ideas of reflection, refraction, and its application part. Clear? Right. Let's move ahead. Now, we discussed, with respect to reflection, we discussed spherical mirrors, meaning I am interested in reflecting the light. But when I talk about refraction, I am interested in spherical lens. That means I have to ensure that the light is incident on the lens, and either it is focused at one particular point or it converges from that particular point, so that I get, say, enlarged image, or I can focus and look at minute things from a larger perspective. So I use lenses for those, spherical lenses. What kind of spherical lenses do we find? Majorly 2 kinds. That is the convex lens, not mirrors lens, convex lens and concave lens. Now, convex lens means the lens which is bulging at the middle. There is a bulge at the middle. Concave mirror, they are thinner at the middle and thicker outside. They are thinner. You do not find bulge here, you find thin surface, thin face here. And in general, the convex lenses, they converge. They are called as converging lens. If you look at this ray diagram, you see that the light is incident on the lens and it converges at one particular point on the focus. Whereas a concave lens, it ensures that the incident light is diverged. Clear? So convex lens and concave lens. Now lens, they are based on refraction. Again, from here also for your reference, there have been some ray diagrams shown so that where is the image formed. With respect to a concave lens, if the object is at infinity, then the position of the image is at focus f1, and if the object is between infinity and optical center O, optical center O is this, optical center O is this, and optical center O is here, because it does not talk about the radius of curvature, it is connected with optical center now. So if you look at the ray diagram, you see that the object is at infinity and the image or the refracted ray is diverged, but its image is received here at f1, and that image would be highly diminished, just point sized. Same with the other idea, where if the object is at a finite distance, you will find that the image is formed somewhere between f1 and the optical center. It is also diminished. So for a concave lens, we receive diminished images, but they are virtual and erect images. Concave lenses. Convex lenses, when you talk about convex lenses, there are different positions, and here you can get different characteristics, or you can get enlarged images, you can get same side images, you can get diminished images, but ultimately you ensure that the whatever is your application, you get on the basis of that, you can get real or inverted image, or you can get virtual, erect and enlarged image based on different configurations, right? These are the ray diagrams for that. You can refer that. Again, from UPSC civil services perspective, there is no need to focus too much on this aspect. Very similar to how we discussed with the spherical mirrors, the spherical lens also have exactly same lens formula, very similar to the mirror formula. The lens formula is same, but please remember, it's not 1 by u plus 1 by v. It is 1 by v minus 1 by u, that is equal to 1 by f. And the magnification formula is exactly same. Magnification means the height of image divided by height of object, and you can again derive it in form of v by u, but it is not minus v by u. Please remember, the magnification formula for a mirror was minus v by u. Here it is plus v by u. Right? All right. These formulae are very useful in numericals, and numericals, we do not find them in UPSC examination. We do not get them in UPSC examination. But just for your reference, so that you have an idea what is the meaning of magnification, I'm telling you this. But more importantly for us is another concept. It is this. We'll talk about this in some time. But before that, the power of lens, the formula of power of lens is 1 by f. The power of lens, it is based on this lens formula. You calculate this f, 1 by f, this gives you power of lens. And when you put these lenses in series, or when you use them in collaboration, you do know that for a optical microscope, or for a telescope, or even for that matter for these lenses, you must have seen the combination of different lenses. That's why I told you, when you go to an optical place or you go to an ophthalmologist, what they do is they put a template spectacle on you. They close one side to check the power for one particular eye, and what they do is they keep one particular lens and they say, is it clear? Then they do a trial and error basis. Sometimes they even put 2 to 3 types of lenses as a combination. Now when they are put into combination, please remember, when we use them in some combination, then the power of lenses, it becomes sum of those lenses whatever are placed. So during your eye testing, you must have seen this. I'm quite sure many of you must have felt that the doctor will ask, is it clear? He asks, is this lens clear or the other lens clear? Then he will go for some sort of combination and then ask you, is it much clearer? Whatever suits best for you, you get that as your spectacle. I am quite sure that people who wear spectacles, they understand that. People who wear goggles for style, they will not get this too much, because once you get that eye testing done, I'm quite sure you'll understand this slide. in a better way. All right. Now, apart from that, the important idea for us is to understand where spherical lenses are used. You must have seen in our day-to-day life, spherical lenses are used manywhere. Both convex and concave lenses, they are used in spectacles. You must have seen concave lenses in spectacles also. But you must have seen lenses used in microscope, magnifying glass. In our childhood, we used to take this magnifying glass and focus the sunlight. That's the classic idea of a convex lens. You hold that magnifying lens in front of sunlight and you will see that the sunlight is focused at one particular point, and after some time, if you incident that particular light on a paper, that paper burns. Why? Because you're completely focusing all the sunlight at one place. Heating will take place, right? Now, apart from that, you must have seen in telescopes, projectors, camera lenses, many convex lenses are used. Apart from that, concave lenses are used in binoculars. They are used in flashlights. They're used again in telescopes. In telescopes you use different combination of lenses. In eyeglasses you use concave lenses. All right. So lenses have multiple applications. So make sure from next time, whenever you're outside or whenever you are getting some sort of application, check what is it. All right. Say what kind of lens is it, what kind of image is being formed. Say for instance, there is a small assignment for you, right? What kind of lens do we use, say, in a keyhole? Do you have a keyhole at your home? Say if anybody rings your doorbell, what do? You go and peep through the keyhole and check who is it, and you will see that the keyhole is just this, but there are many keyholes in which you can see the complete person outside. So what kind of lens is it? Do let me know in the comment section, because questions like these only come in UPSC based on day-to-day activities, based on common sense. All right. So that's the end of today's chapter. We'll meet again in the next or the subsequent chapter. All right. Thank you very much for watching. And if you have liked this video, or if you have any queries, any doubts, if you want to connect with me, you can always follow me on this particular ID @ Rahul Sai 222. Thank you very much. Jai Hind.